Hi guys, it's Veterans Day, and yep, I am sitting in my kitchen and I am going to record Chapter 7, Section 6, Quantum Mechanics. So we are going to compare the Bohr model of the hydrogen atom to the quantum mechanical model of pretty much any element, since the Bohr model started getting ripped apart with the advent of better technology. Things like where they thought there were only one color line, there was actually two. Instrumentation got a little more savvy. So 50% of his theory stayed and 50% got canned. The Bohr model said that energy is quantized. Quantum mechanical model kept that. A quantity of energy is emitted when an electron moves down an energy level, and a quantity of energy is absorbed if the electron is moving up an energy level. So that stayed. It caused the emission of light, aka a photon of light or a mole of photons of light, and that stayed with the quantum mechanical model. The energy of the orbitals are easily calculated. That went. It was not true. Schrodinger wave equation is a very complex differential equation, calculus type mathematical computation that we cannot calculate the energy of the electron at all. All we can get from the Schrodinger wave equation is a couple of properties of the electron. Bohr was under the impression that the electrons orbited the nucleus in perfect concentric rings that he called orbits, and that he thought you could calculate the radius. If you recall from the last, he thought this was the radius of his orbit, and that also went. So 50-50. In the quantum mechanical model, the electrons are in orbitals. It's a probability map. Wave nature of matter, we already discussed this in one of the other videos. De Broglie basically theorized that if light can have material properties, matter, aka material, should exhibit wave properties. Heisenberg uncertainty principle you had first year. Heisenberg showed that we can never actually know the speed and direction of the electrons. We cannot, with 100% accuracy, calculate the position and speed of an electron. Now that's Bohr model thought we could. The quantum mechanical model says we can't, and this is still the model we use today. We can only calculate the probabilities. So this whole quantum mechanical model is kind of like Vegas. You can only calculate the probability of where the electron might be with 90% accuracy. Erwin Schrodinger developed a mathematical treatment into which both the wave and particle nature of matter could be incorporated. What you see on the right is a three-dimensional probability map. What this probability map is telling you is there's a 90% chance of finding the electron in this very dense area and 10% on the outskirts. Now keep in mind this is three-dimensional, so this is a very spherical looking shape, which actually is going to, as we get deeper into this video, represent the s orbital. I kind of equate them to like scatter plots, and this theory that Schrodinger came up with is called the quantum mechanics. This is actually the Schrodinger wave equation, and these are symbols from differential equation, from high-level calculus. I recognized some of these when I took calculus class, but that was so long ago. I don't even know what most of them are anymore. Thankfully, we don't have to use this equation. Thankfully, we are only going to glean 4 pieces of information about the electron from this equation and not use this equation to calculate the energy of an electron. All right, quantum numbers. Quantum numbers are the 4 pieces of information that come from the Schrodinger wave equation calculation and describes the location of the electrons inside an atom. Principal quantum number n describes the size and energy of an orbital. Angular momentum quantum number, which is a cursive L, describes the shape of the orbital. This is also called a subshell. Magnetic quantum number is m sub L, describes the orientation of the orbital in space, the direction it points, and don't forget this is all 3-dimensional, so you're talking x, y, and z. And finally, the 4th one is the spin quantum number, which describes the spin of the electron inside the orbital. And of course, that only has 2. It's either spinning clockwise or counterclockwise. All right, rules for quantum numbers. N, the principal quantum number, can be 1, 2, 3 to infinity. A couple of things to remember. N will never be a 0 or a negative value. L, 0 to n minus 1. In other words, 0 to 1 less than n. In each one of these is dependent on the previous. So L comes after n. L is based on n. L will be 0 to a number less than n. All right, a couple of things to know about L. L can never be equal to n. L will never be negative. And L has alphabetic designation also. S, P, D, F, G, etc. M sub L. M sub L will be negative L to positive L. This is an arbitrary pick. It could also, in college, be positive L to negative L. Negative L to 0 to positive L. And then spin is nice and simple. Now again, something we picked arbitrary. A positive 1/2 will be a clockwise spin, designated by the up arrow. A negative 1/2 will be a counterclockwise spin, designated with the down arrow. Please put these into memory. An orbital is technically the probability map. The scatter plot I showed you earlier, humans put a defined edge onto it. That defined edge encompasses or encloses 90% of the scatter plot. And that scatter plot has different shapes. I showed you one already. I'm going to show you a few more. Orbital types or sublevels. S, P, D, F, that corresponds to 0, 1, 2, and 3. Don't forget that L can be 0, 1, 2, 3, 4. So sublevel L can have numeric designation and alphabetic. Please make sure you know how to toggle between the two. All right, S orbitals. L is equal to S. Also stands for L being equal to 0. That means M sub L is 0, 1 orbital. The value of L for S orbitals is 0. They're spherical in shape. That means that the probability map is a 3-dimensional spherical probability that the electron is 90% in that sphere. And of course, the further from the nucleus you get, the larger you get. Notice 1s, 2s, 3s, and the nucleus is dead center, and the 3s is a larger orbital. All right, p orbitals. L is equal to p correlates to 1. M sub L will be negative 1, 0, positive 1. And M sub L also has alphabetic and numeric designations like L, but we rely on the numeric ones way more, and I'll show you why in a minute. P sub X, p sub y, and p sub z, and the orbitals look like dumbbell shaped, which is what you see here at the bottom of the picture. We humans kind of put a defined edge on it, because in reality the probability map looks more like this shadowy area, and you have a lobe that's on the z-axis, and a lobe that is on the x-axis, and a lobe that is on the y-axis that looks like 3 dumbbells. So the p orbitals basically have 3 total orbitals, and each one lies on an axis. All right, d orbitals. This is L is equal to D, or 2. Again, remember that L has an alphabetic and a numeric designation. When L is equal to 2, M sub L is -2, -1, 0, +1, and +2. And again, M sub L also has numeric and alphabetic designations, but here's where the alphabetic designations get kind of ugly. Let's see, you've got 4 clover leaves and a dumbbell with a donut. So the alphabetic designations are technically lying between and on the axes. And 4 of them are clover leaves, and 1 of them is a dumbbell with the donut. So technically speaking, this -1, 0, +1, and +2. And I might add, these are degenerate, which I want you to write down. Degenerate means they are the same energy level as long as they're the same n. They will be the same energy level. F orbitals, this is when L is equal to F, or 3. M sub L will be equal to -3, -2, -1, 0, +1, +2, +3. And how many orbitals is that? 7. 1, 2, 3, 4, 5, 6, 7. And again, that alphabetic designation for M sub L gets a little ugly, so we really stick with the numeric one more than anything. There are 7 orbitals with all different types of orientations. They're all over the place. You can imagine what the g orbitals look like. So here's a couple of pieces of information. You have n, which is the principal quantum number, L, which is called the sublevel, M sub L, which is really the orbitals, and then M sub S, which is the spin. This tells you energy and size. L tells you shape. M sub L tells you axes. M sub S tells you spin. L has an alphabetic and a numeric designation. M sub L is the total number of orbitals, the orbitals that are in L. M sub L also has numeric and alphabetic designations, but we stick with the numeric for reasons I just showed you. So here's what I want you to write down. L, either 0 or S, 1 or P, 2 or D, 3 or F, 4 G, and it could go on, but we really usually just stop at F. When L is 0, M sub L is 0. When L is 1, M sub L is -1, 0, and +1. That is 3 orbitals. When L is 2, M sub L is going to be -2, -1, 0, +1, and +2. That is 5 total orbitals. When L is 3, M sub L is -3, -2, -1, 0, +1, +2, and +3. That's a total of 7 orbitals. When L is 4, m sub L is -4, -3, -2, -1, 0, +1, +2, +3, and +4. And please remember that m sub L really represents the axes, so it's kind of an extension of L. Not only is it the shapes, but it's the axes they're on too. And that's 9 orbitals total in the L being equal to 4. Maximum number of electrons in each one of these. Please remember from first year chemistry that you can put in a maximum of 2 electrons per orbital. So this is 2, 6, 10, 14, and 18. So this is a little practice with the energy levels, the sublevels, and the orbitals. And there's a difference between the sublevel. The sublevel indicates the entire L, whereas the orbital is an individual axis. So be careful of the terminology. So for example, the very first question, how many electrons can an s orbital hold? This is literally asking you about one axis, one axis. So only 2. For the second question, it's saying how many electrons can be in the actual sublevel. The entire sublevel means all the axes. So for example, when you're talking about the entire orbitals in all of S, there's only 1. So 2 electrons. In the entire sublevel of P, there are 3 orbitals. 2 electrons per orbital, 6. D, there's 5. F, there's 7. So that correlates with those. The third question, how many electrons can energy level number 1 hold? And I'm going to show you a little shortcut for this guy here. Energy level number 1 can hold 2 electrons total. Number 2 can hold 8. Number 3 can hold 18. And number 4 can hold 32. So these are just some examples, right, pertaining to this guy right here. All right, there's a shortcut, and it only works if you're just given n. If they give you any L of any kind or any m sub L information, this shortcut will not work. It only works if you're given just n. N squared will give you the total number of orbitals in that energy level. N squared times 2 will give you the maximum number of electrons. Now when we get into electron configuration, don't forget, you'll have that number of orbitals, but they aren't always necessarily filled. There isn't always going to be a maximum number of electrons in those orbitals. So this is just basic information when they start asking you about energy levels. And I am going to do an example. Pauli exclusion principle: in a given atom, no 2 electrons can have the same set of 4 quantum numbers. An orbital can hold only 2 electrons, opposite spin. You've had this before. This was first year chemistry. When we get into electron configuration, we'll be using Pauli exclusion, Hund's rule, and the Aufbau principle a lot. All right, so we're going to practice. Writing quantum numbers, and all I'm really going to do is give you a. Let's say, for instance, it wants n is equal to 3. All right, when n is equal to 3, that's the only piece of information they gave you. There are a couple of things you can do. When n is equal to 3, L is going to be equal to 0, 1, and 2. M sub L, when L is 0, M sub L is 0. When L is 1, M sub L is -1, 0, +1. When L is 2, M sub L is going to be -2, -1, 0, +1, and +2. All right, notice the long way, there are 9 orbitals. And each orbital can hold 2 electrons, therefore a maximum 18 electrons in the energy level number 3. Shortcut method. Only when they give you just the energy level. N squared. 3 squared is 9. N squared times 2. 3 squared is 9 times 2, that's 18 electrons. Notice, same answer as what I did longhand. Is I am going to write out so what I'm going to do is I'm going to write out the 4 quantum numbers for maximum number of electrons in n is equal to 3. In order of fill, which we will discuss a little more later, but just follow along right now. This is going to be 18 electrons. So this is going to be 18, and what we like to refer to as electron addresses. Okay, this is the 4 principal quantum numbers for 18 electrons, what I refer to as 18 addresses. Every one of them different. The first column is N, principal quantum number, energy and size. The second column is L, shape. The third column, M sub L, the orbitals, axes. The fourth column is the spin of the electrons, either spinning clockwise or counterclockwise. Plus 1/2 means clockwise, negative 1/2 means counterclockwise. Alright, so in order of fill. So what you need to know is this is the 2 electrons in the 3s. And these are the 6 electrons maximum in the 3p. And this would be the 10 maximum electrons that can be held in the 3d. And I really kind of wish I hadn't picked n is equal to 3 because that's a lot of electrons and that's a lot of addresses to try to keep track of. Let's do another short example. I'm going to do something different. I'm going to do, I want the 4 quantum numbers for 4p electrons. Alright. Well, this really, you can't use the shortcut for this. This really gives you something more specific than just n is equal to 4. This only contains 6 electrons. So this is going to be a lot easier to do. Alright, so this gives you a more specific piece of information. Instead of just saying n is equal to 4, this is actually n is 4, but L is 1. So your M sub L is going to be negative 1, 0, positive 1. 2 electrons per, so you get a 2, 4, 6, 6 electrons total, max. And each electron, there's their addresses. So we're going to practice this in class some more too. But you have to memorize the rules. N, L, M sub L, M sub S. Energy, size, shape, axes, spin. So those are you're going to have to put in your head, and we're going to practice this for a while. Especially make sure you understand when they're talking sublevel versus orbital. Sublevel is the entire P. orbital is just one of the three requesting. And that's the end of that one for now.